Alright, this video is going to be a quick recap of resonance structures and exceptions to the rules. So, a quick thing about resonance structures is they are structures that each fulfill the requirements of all the atoms being happy, but how they do it is different. Like normally with CO2, we're going to think of it in this form, but CO2 could technically be written with a single bond on one side and a triple bond on the other side. So to do formal charges, we're going to look at the number of valence electrons they're supposed to come up with. Like oxygen comes with 6 valence electrons. Carbon comes with 4 valence electrons, and oxygen comes with 6 valence electrons. We did the same thing over here. And then we're going to look at the electrons that are actually assigned to that atom. Like for the oxygen here, I would say it has 1, 2, 3, 4, 5, 6. It has the 6 electrons that it's supposed to come with. Carbon, it has 1, 2, 3, 4. 4 assigned to them. Yes, he's sharing 4 more, so he has a total of 8 around him, but there's like 4 electrons assigned to him. Same thing with oxygen over here, there's 6 electrons assigned to him. So then if I take this and I subtract 6 minus 6, I'll get 0. 4 minus 4, I'll get 0. 6 minus 6, I'll get 0. So this is a good looking structure because everyone came with a set of valence electrons and they all are assigned that number of valence electrons. Well, if we look at this other side, I've got oxygen here that has 1, 2, 3, 4, 5, 6, 7 assigned to him. 7 assigned to him, so 6 minus 7 is a negative 1. Carbon here still has 4 assigned to him. That's a 0. But this oxygen is 1, 2, 3, 4, 5. So 6 minus 5 is a plus 1. So what that means is if I'm looking at all the electrons, I'm kind of deficient by 1 electron here, and I have 1 extra electron here. Well, oxygen is very electronegative, so this oxygen feels totally fine with having an extra electron. He kind of likes it. But having this oxygen deficient in it is really making him unhappy. So this structure is not the dominant structure of these resonance structures. It is less effective, I guess I would say. So if you want to look at something like CNO, here are the different structures of CNO. What you'll do is you'll draw a little stop structure for one of these, like maybe you'll most likely do this middle one. And then once you see you've got a double bond going on, you just want to rotate the bonds around. And that's how you make resonance structures. I'll move a single bond here and a triple bond here, and do the opposite of here. So resonance structures are really just find a good one, which you know how to do, and then rotate the bonds around. And then I'm going to be assigning formal charges, and that's what the numbers are in red. And so then I would ask myself, well, which one is the dominant structure? Which structure is really happening the most? The one that's happening the most, I think in this case, is closest to the zeros. Got that. So that leaves me with these two. And then I want to find something that has the most electronegative atom has a negative charge. So oxygen is more electronegative than nitrogen. It goes F for the most electronegative, then O, then N. Oxygen is the most electronegative, so he wants to have the -1 charge. So this structure right here is the most dominant structure. Right? Okay. So then our other question is, how do we know that resonance actually occurs? Like, why do we know that the bonds kind of move around? So I would have you draw ozone. Here's what ozone looks like. And so they really do look the same. Like, it just seems like you just turned your paper around. But that's not exactly what's happening here. What's happening here is if you take a look at this thing, it looks like they have the exact same bond. We can actually use different kind of equipment and find the bond length of these things. Angstrom is a type of length. So this bond length is 1.278, and this bond length is 1.278. That means the bond lengths are the same. So the question would be, like, how could the bond lengths be the same if we know that they have a double bond here and a single bond here? Like, if I think about a double bond, it should have a shorter bond length. A single bond should have a longer bond length. So if I had got this molecule off of the machine, I would see one bond is short and one bond is long. But really, we know that they're both the same bond length, which means that this is like a resonance structure here. That means the electrons are sort of doing this, but they're sort of doing this at the same time at any one moment in time. The actual structure of ozone is like a mishmash of these two. So if you can take both of these pictures and kind of put them on top of each other, that's what the actual ozone looks like. So the bond length for this isn't like a bond length of a double bond, so like a short one and a long one. The bond length is like a bond and a half-ish, because if you mash these two together, you really have 3 bonds going on here between 2 parts. So this is like worth a bond and a half, and this side is worth like a bond and a half, which is how we can see that we have the same bond length. The bond length wouldn't be equal to 1 bond or a double bond. It's like a bond and a half. Okay. So that brought us these resonance structures so that we could draw all the different resonance structures and then decide which one is the dominant one. You'll find the answers online for that. Exceptions to the octet rule, there are 3 different kinds of exceptions. The first one is talking about things that are less than. If you draw BF3 using the proper rules, it would come out something like this. But you can see that F has a +1, and F with a +1 is very, very icky, so that can't possibly be what it really is. These things exist, but the dominant structure is this boron structure with just 3 of them. So the moral of the story was this fancy rule, which I'm not even going to read for you because I don't think it's important enough to memorize. What's important to know is that there are exceptions to the octet rule. The first one is that hydrogen needs 2 electrons and boron only needs 6 to be happy. Done. First rule is you can have someone who has less than the number of octet, boron needs 6, hydrogen needs 2. Moving on. There are times that we can expand our octet actually, and that's how we can have phosphorus have 5 things around him. The only way to do that is if he goes into his D block, which is more than you really need to know. You just have to know that 5-sided things and 6-sided things exist. And sometimes it's going to make things better. So if you look at this structure here, here's normal phosphorus, and if you draw it like phosphate, that's totally fine. Or you could draw phosphate this way. So this one has 1, 2, 3, 4, 5 bonds. Phosphorus can do that. Sulfur can do 6 bonds. So these are totally fine, and if you look at the formal charges on it, this one on the right has a nicer formal charge. But this one on the left is nice because it follows the octet rule. It doesn't go past the 8 electrons in the phosphorus. So which structure is the dominant structure? That's up for debate. So I have no real answer for that. That's why I have to look at the question of the AP thing. Does it say, tell me which one's better according to formal charges? If it does, this one's your answer. If it says, tell me which one's better according to Lewis dot structures, that's talking about the octet rule, then this one's better. Odd number of electrons, they happen. I would have to say that we're not going to find those on the AP test. I just don't think it's likely enough. Knowing that they happen is all you kind of really need to know. I gave some exceptions to kind of draw so you could practice them. Are they hard? Yes. You'll probably have to look at the answer key, and that's okay. The likelihood of these exception ones to be on there is very low. The likelihood of being things to have I think I hit pause somewhere in there. So my summary slide of this, in case you missed it, is the idea that sulfur comes with 6 electrons. So he can expand his detect to make 6 bonds. Phosphorus comes with 5 electrons, 5 valence electrons, so he can easily send his out to make 5 bonds. These are 2 things that do exceptions, but if you don't have to, then don't. Keep yours to keeping just 8 around there. So only do the expander tet if you have to. Like a time when you have to would be like PCl5. Then you have to in order to have 5 chlorines around. Kind of like xenon or chlorine or fluorine. If you have to have them do it, they will. This is the noble gases. They'll do it if they have to. But ideally, we don't want to have them do it. We want 8 valence electrons. If they have that, they're good to go. We just do it when we have to. I think it's unlikely you're going to see chlorine or fluorine in the middle. These xenon ones, that could happen. Most likely sulfur and phosphorus are going to expand their tet, but they're unlikely for these